example 7. So in this example, I try to show you the inverse response. Actually, I show you this example in the lecture, and it's for a boiler for a distillation column. And here the steam pressure change. So here the steam pressure that change and then this will actually this is the heating up the boiler, right? And then there's two processes we need to pay attention that will influence the liquid level in the boiler. So the first one is in process 1, steam pressure will increase the vapor flow, right? Because we increase the steam pressure, and then we increase the heating power, and then most steam will be generated in a short time, and then the vapor flow rate is increased, and then this will cause a rapid spillover of liquid from the trails to the boiler. So this one you're going to have spill over, and then this will increase here the output of resistance, the liquid level in the boiler, right? This is fast response. And another process here is because the heating power increases, so the evaporation, right? Evaporation, and it increases, right? So therefore, and the more vapor will be generated, and then which will lead to lower liquid level. So therefore, decrease. This will decrease the liquid level, right? But this is slow process because it takes a time, sometimes, to get the evaporation done, right? So here I want to show you using Simulink and the liquid level of tank in the boiler, right? Yeah. So K1 is equal to 3, K2 is equal to -6, and tau 1 equal to 1, and see K1 K2 they are opposite, right? And then tau 1 is small, very fast. Tau 2 is 10, is large, right? Slow, right? So based on that, we might have the inverse response, right? Okay. Actually, I show you one formula that you could use to determine whether a process has inverse response or not, right? So I think it's K1 tau 2 plus K2 tau 1, right? And over K1 plus K2. If this is negative, and then means there's a inverse response, right? Actually, I asked you to do one in class assignment. And then yeah, you did a great job, and then you calculate that this actually in this example, and this term is negative, so there will be an inverse response. Here I want to show you in Simulink and how to get the output profile, right? Actually, I think this is very straightforward because this example is actually is simpler than the example I show you, right? Those are previous example I show you. So now let me show you how to build the model, Simulink model. So we go to Simulink, and then File, and then New, and then Model, and then so we need to get two first order transfer function, and then add them together, right? To get these two transfer function, add them together, and then that's it. So we get to transfer function here, transfer function continues, right? And here calculate some function. We zoom in here a little bit, and then we copy it. Okay. Then first one we get here 3, here s and 1 plus s plus 1. The second one is -6 again, and time constant is 10. Right. So the step change here, the step, let me see, the step change is 10. Okay, just 10, and magnitude change in the steam pressure. Okay, this in the pressure. Right. So we want to see what is the output change, right? How much the liquid level will increase or decrease. Alright, we add a step, go to the sources, and step. So at the same time, we only need to add the time signal, clock, okay, and then we it's a bit bigger, right? And then this clock move it around, and then link them together. Okay, now we want to set it up, and then we need to add this first order together. Go to the mass operation. Here's the add. Right, so we add them together. Add this one, and this one, and then we save the output, the sink. Right, and this is a workspace. So it's larger. So this one we're going to, let's see, just up, then you can see them together. Like this one, you get link them, change this one to Y, and the format is array. Okay, then we add another workspace here for the time here, and here's a T, and again it's array format. And then if you want to in developer one, you're going to add display, and also you can add the scope, but they are not necessary, right? And then save it. Right, actually you should save it at the beginning. Example 7 Simulink. Save it, and the simulation, you're going to run the simulation for how long? Simulation should be run 80 minutes. So 80 minutes, 80, and then the steps change is the step time 0. The final value is, because we have 10 psi change, like 10 psi. So this is a deviation term, right? So we just care about the change of the liquid level. So here the output actually is a deviation variable. Okay, so run the simulation, and then we get a result. Before we show the result, and then we can see the profile from the scope. See, the system gets started after 80 minutes. Right now we want to plot the output profile, so we go to just type this 3 and lines here, but we need to build a new function here, a new script here. So you just plot, save it first, Control and S. Here 7, and then 7, right? And plot TY flat light width 2 S label time minutes. Right, and then is font size 12. Then copy this one for the Y label. Y label, and then change the Y label here is the Y, the liquid level, and the change of liquid level M, right? Save it, Control S, and then we could type main example 7. So here's the profile you're going to get. See, right? Exactly the same as the one I show you here. Right? This if the system and this one is start state value, right? No change of the steam pressure, and so the liquid level should not change anything, right? However, now steam pressure increase, and then the liquid level increase first, and then decrease, and then see the decrease. The final decrease value is minus 30. Actually, we could calculate this, right? So you can see we have two steps, two first order, another first order, right? So you have K1, you have K2, is delta U, right? So the start state change because the because our process is K1 times delta U, and the steady state change of the output because of the second process is K2 delta U. Now here you get 6 and 10 psi, and here's minus 6, 10 psi, and then you get 30 minus 60, and then it's minus 30. So you can see minus 30 here, right? Okay, so based on the transfer function, the gain, and then you also actually you could calculate the change of the start state for the whole process. But you do see the inverse response here, right? Okay, we are done with example 7.